each major component and have a brief idea of how they work. First of all, is the light source. Now, we already said that we're going to use halo cathode lamp, which is basically using element to detect element. What does that mean? So if you look at the structure of the halo cathode lamp, the cathode is constructed with the metal whose spectrum is desired. Okay, so for example, your next lab is copper lab, meaning that you're interested in detecting the concentration of copper in the solution. So copper is, the copper spectrum is desired. And as a result, you will have to use a copper lamp. And for a copper lamp, this halo cathode here is constructed by copper, okay? And the mechanism here is you will analyze inert gas to high potential in this lamp. For example, at 300 volts, the argon gas will be converted to argon plus and generate electrons. And then when the argon cation heat the cathode, so the argon is here, is being ionized. And when the argon ion hits the cathode, some of the deposit element is excited and dislodged into gas phase. And this excited element relaxes to ground state and emits characteristic radiation. And this characteristic radiation is what we want to detect copper. I see a question here. So, so here we're able to change the halo cathode depending on what metal we want. Yes, you have to change the cathode every time if you want to change to a different metal. And we have only limited number of lamp in this department, so it's not like you can do a universal detection with this instrument. So it's not covered in this class, but I'd like to mention that you can use mass spec to do a high throughput elemental analysis. We call it ICP-MS. So compared to this one, you can actually simultaneously detect different elements at the same time. Okay, so coming back to this is the process how the cathode lamp works. But in a word, you are using the same element to construct the lamp, and you're using that element to generate radiation that has the wavelength that is required for detecting the interest element. So the characteristic radiation will generate sharp lines specific for element of interest. When I say sharp line, it means that if I have a spectrum there, right, at a specific wavelength, I have a very sharp line. But in realistic, it's not exactly a sharp line. So in realistic, what you would see is something like this. Okay, so let's say this is a wavelength. So ideally, we want to see those single lines, right? So we can like make sure that this light can only be absorbed by copper. But realistically, you will have a small distribution here, right? The center is the desired wavelength, but you will still have a little bit distribution on both sides of that line. Okay. But anyway, the take-home message here is the hollow cathode lamp. You use the same element to detect the element of interest because it will generate characteristic radiation, which is sharp enough for specifically for the element of interest. Okay. The downside here is it can be expensive. You need to use different lamps for each element tested. Okay. Now, we talked about the light source. What about the sample part? Remember, we said that this technique, you need to work with atoms. But if you think about the original format of your sample is, for example, it's copper dissolved in solution. So you have a large amount of solvent molecules and you have other analytes. Right? You have other molecules or ions or in the whole sample solution. So you have to go through a process to convert a solution to free atoms for the light to interact with. And how many different steps we involve here? Okay, this is a schematic shows the general steps. We have the original sample. It will go through neutral first to be converted to spray, and then it will go through desolvation to remove the solvent. They will become dry aerosols, and then volatilization to form free atoms. Okay. First of all, what is nubilization? Nubilization is you convert the sample solution to fine droplets by spraying through thin nozzle or passing over vibrating crystal. But anyway, it's just you have a large chunk of solution, you just convert them to small droplets so that it's easier for the following steps. Okay, that's a nubilization. And then desolvation is by heating. So you're heating the droplet to evaporate off solvent and just leaving analyte and other matrix compounds. Right. So for example, the most common solvent we have in analytical analysis is water, right? By heating the droplets, water will evaporate out and it will not interfere with your detection. And then is volatilization. You will convert solid analyte metric particles into gas phase. Okay? And then dissociation, break up molecules in gas phase into atoms. So what it means right here is after volatilization, you will still have some molecules in the atmosphere, and you want to convert you want to break up those molecules and make them all in free atoms, because only the free atoms can absorb the light, the specific wavelengths we have here. Okay, now move forward. So what we have here is this is it matter what solution our sample was dissolved in, like basic, acidic, or organic solvent? So most of the cases, the solvent won't interfere with your metal ions because they don't absorb the wavelengths of light there. In most cases, the interfering ions are those metal ions that can absorb at very similar wavelengths of light there. But if you use organic solvent, it might not be good for the system. It depends on what system you have. Like if you always use a very acidic solution, it might cause damage to the pipeline. But theoretically, they should not interfere with your detection because the absorption is totally not interfere. Okay, here is just two types of flame atomizers. The first one, this is the typical one we use in our test. You can see that if you remember the flame picture I showed you, it's actually you see it's a long dimension, right? So that's what happens here. The flame will be generated here, right? The sample capillary goes in here. We have a nebulizer with sample oxidant and fewer are mixed here. And then the only finest solution droplets will reach the burner. This is the burner, right? Most of the sample actually is being collected in waste, right? Because you cannot have a lot of them being burned because that will not be efficient to generate the free atoms. So actually only a very small amount of droplet will actually go through the burner and generate it to the free atomic form. So it will provide flame And as I mentioned here, it's a long path length. Why do we want a long path length? We want the light to interact with the sample completely. So light will come from one direction and exit from the other direction. And when it's travel along this long path length, it can interact with the free atoms completely from the sample.
Professor, are you still with us?
Yes,
I think she might have cut out.
am I? Hello,